Hi, this is Wagner Kamakura, and I'm going to show you how you can run logistic regression using my analytic tools for Excel. But before doing that, I want to give you the intuition behind logistic regression. At this point, I assume that you're already familiar with linear regression. And linear regression is somewhat related to logistic regression because both of them produce a linear score as a function of predictors. The main difference is that in linear regression, this linear score is a direct prediction of the dependent variable. You have a continuous dependent variable, and the score is already an estimate of the dependent variable or a prediction for it. In logistic regression, the linear score measures the propensity for the event, for a binary event, or its log odds. So in this case, the score is equal to the log of the probability that the event will happen over the probability that it won't happen. And with a little math, you will find out that the probability of the event is equal to the exponential of the score over 1 plus the exponential of the score. And we're going to see how this works using a fairly simple example. In this example, we have 768 female patients that were tested for diabetes. And the dependent variable is a result of that test, whether the patient was diagnosed as a diabetic, 1 if yes, or 0 if not. And the predictors explaining that propensity would be the number of pregnancies, glucose level, blood pressure, skin thickness, insulin, body mass index, diabetes, pedigree, function, and age. Before doing anything, let's run a regression, just a simple linear regression using Excel. Go to Data Analysis, Linear Regression, or Regression. And our dependent variable will be has diabetes, 1 or 0. Our predictors, or input range, will be pregnancies, glucose, etc., down to age. We have labels, and we're going to save the regression coefficients on a new sheet. And here we have the linear function, the coefficients for the linear regression. I'm going to insert 2 rows to copy the regression coefficients that I'm going to use as a starting point to build our logistic regression. Here we have the intercept and the weights for each one of the predictors. So I'm going to compute the score here, the score for each patient. So the score for each patient will be equal to the intercept plus some product of the weights, regression coefficients, and the predictors for each patient. Because we want to copy this formula all the way down for every one of the patients, I'm anchoring the coefficients so that the same row 2 will be applied to every patient. So there we have the linear score, which right now is the linear regression score because we are using the linear regression coefficients. Now I'm going to calculate the probability of diabetes as x of the score over 1 plus x of the same score. First patient has a 65.57 probability of having diabetes. Now we're going to calculate the likelihood, not the likelihood of having diabetes, but the likelihood associated with the actual event, whether the person has or not. If the person has diabetes, which is the case for the first patient, then the value of the likelihood should be the probability. On the other hand, if the patient does not have diabetes, the probability should be 1 minus the probability of having diabetes. So that's the likelihood for us to see the difference between having diabetes and not having. In the second case, the patient did not have diabetes, and the probability of having diabetes is 0.501, So the likelihood of the event is not having diabetes, is the complement of that, 0.498. And we're going to calculate the log likelihood, which is just the log of the likelihood. Now we can copy these formulas for every patient, each one of the 768 patients. So we know that these coefficients here are the regression coefficient, linear regression coefficient. But we wanted to estimate the logistic regression coefficients. We wanted to find what are the coefficients that make the likelihood of the sample. In other words, the product of these probabilities here, the largest possible. But we're dealing with probabilities. So when I multiply 768 probabilities that go from 0 to 1, that product is likely to be very small. That's why we use log likelihood. So that now, instead of multiplying the likelihoods, I can calculate the sum of all the likelihoods. Now we can find what are the weights, those weights here that I'm highlighting. What should be those weights so that the sum of log likelihoods is the largest possible? In other words, what would be the set of weights that will make the observed events most likely? And we can do this using solver. So what is our goal here? We want to maximize the log likelihood, which is on cell N1. We want to maximize, and we want to do this by varying the range that I had highlighted before, these cells here. We wanted to find what is the combination of weights, intercept, pregnancies, glucose, etc., that would produce the highest log likelihood. And we don't want the coefficients to be non-negative. Right? We wanted the coefficients to be anything they want to be. So we do this and run solver. And you can see that the likelihood now is not as negative. Went up from minus 500 and something to minus 361. So now this score here is the logistic score. So those are the scores that measure each patient's propensity of being diabetic. They are the log odds of being diabetic based on the patient's number of pregnancies, glucose level, blood pressure, skin thickness, etc., etc. So these now are our logistic regression coefficient. These are our log odds, or the logistic scores, and this is the maximum log likelihood. To see how well the logistic regression predicts the event, having or not having diabetes, let's copy this range here, all the data up to our score, to a new sheet. We're going to create a new sheet. And our goal is to see how well this score discriminates between people who have diabetes and people who do not have diabetes. I'm going to only focus on that variable, dependent variable, and the score. And again, the score is our propensity score, the score that measures the patient's propensity to have diabetes. Let's sort this data in decreasing order of the score. So since the score was computed through a logistic regression, this score measures the propensity. So the patient with the highest propensity of being diabetic is patient number 446. The second highest propensity is patient 194, etc., etc. So let's calculate the cumulative number of patients, the cumulative number of diabetic patients. And so on. And here, let's just count the number of patients. So we have, in this column here, the propensity ranking on column E, and on column G, we have the count of diabetic patients. So for example, if we take the top 20 patients with the highest propensity score, they include 16 of the diabetic patients. So let's transform those two columns into percentage. So here is the cumulative percentage of diabetic patient, and here we have the cumulative percentage of patient. This number is going to be cell D2 over the last cell, D769. And let's make sure that we anchor. And this cell is going to be E2 over E769. And let's make them look like proportions or percentage. So now we can see how well the propensity score isolates diabetic patients from non-diabetics. Let's see the top 20% of patients with the highest propensity include 47% of all the diabetic patients. It shows that the propensity score really helps identify diabetic patients from non-diabetic. And we can see this by plotting those two columns in a scatter plot. Now we can see in this chart how well the propensity score separates diabetic patients from non-diabetic patients. The top half of patients with the highest propensity score account for more than 80% of all diabetic patients. And if we want to quantify that discrimination, we can draw this line here. If you measure the area between the curve and the diagonal and the total area of the chart, that's a number called the Gini coefficient. The Gini coefficient shows the extent to which a high percentage of the highest propensity patients account for a large percentage of the patients with diabetes. Or you can evaluate this chart directly. So the top 70% of patients with the highest propensity score account for 95% of all diabetic patients. Top 40% of the highest propensity score patients account for 75% of the diabetic patients. Now let's see how you run a logistic regression using my analytic tools. For this, let's open my examples. There you're going to find a tab with an example data sample for logistic regression. And running a logistic regression with my tools is fairly simple as long as the data is in the right format. The first column should have an ID for each observation. The second column should have the dependent variable coded as 0 for no, 1 for yes. And then every other column should contain the predictors. And the first row should have labels for each one of the columns. And as long as your data has a simple format, running it is straightforward. You go to Analytic Tools, Logistic Regression. You can do the analysis for up to 80,000 rows and up to 60 predictors. The data is automatically highlighted, but if it's not, you just highlight the range that you want to analyze. We're reading 5,550 rows. We have these predictors available, and I'm going to run an analysis using transactions per month, profit, income, whether the customer has a savings account, credit card account, and ATM card. And we're trying to predict the likelihood of the customer having a certificate of deposits. Click OK. And you can either do a straight estimation or calibration using 100% of the sample, or you can do an automatic holdout test, a predictive validity test, by holding out between 0 to 50% of the data. I'm going to hold out 30% of the data. In other words, we are going to use 70% of the data for calibration, randomly picked, and the other 30% will be used for a predictive validity test. Click OK, and there we have it. We have here the log likelihood. The consistent archaic information criterion is something that you should Google if you want to know about it. It's saying here that we're holding out 30% of the cases for validation. Here's the Gini coefficient that I mentioned earlier in the calibration sample and in the validation sample. Typically, the fit tends to be lower in the prediction because, after all, we are trying to predict the unknown. AUC is the area under the curve calculated under the ROC curve, the Receiver Operating Characteristics curve. That's something also that you should Google if you want to know more about it. Is closely related to the Gini coefficient, but the way the chart is defined is different. So we calibrated the logistic regression on 3829 observations, and we are validating it on 1721 observations. And here are the logistic regression coefficients and the t-value for each one of them. And that's pretty much how you run a logistic regression using my analytic tools for Excel.